Now in probability we'll see the axiomatic approach from where we started. We already seen that there are a number of events that occur, and probability actually attempts, or it is basically into quantifying the chances of the occurrence or non-occurrence of events. So we are going to see the quantification just now, and for that we'll use this axiomatic approach, right? Their axiomatic approach, let me summarize it for you. First thing is, if S is your sample space of random experiment and the probability P is actually a real valued function, the domain is the power set of S. All the subsets which are possible in this for this S, this is the power set of S. The real valued function, the domain is this. The probability is actually a real valued function. The domain is the power set of S, and the range is between 0 to 1. What it means is that the probability is going to come between 0 and 1, inclusive of 0 and 1. So for any event, this probability of any event has to be greater than or equal to 0. If probability of sample space you take, it will be equal to 1. And if E and F are mutually exclusive, that is, they are not going to happen together, then PE union F is actually PE plus PF. And also that this P phi is equal to 0. And if you want to prove this, then just take this expression PE union phi. Let us take F as phi. So that is equal to PE plus PE phi. We use this expression. And what this PE union phi is, if you combine E with phi, you'll get E. So you can cancel it out and P phi is 0. We are going to use this. So let S be this sample space, W1, W2, Wn. These are the elementary elements. So S is equal to Wn to Wn. Now the axiomatic definition lies here, that all the probabilities, the single probabilities, will lie between 0 and 1. 1 and 0 are inclusive. If you combine all the probabilities W1 to Wn, it is going to give you 1. And for any event PA, this is going to be the sum of PWI. This W should belong to this A event, right? So let us take tossing a coin. If we toss a coin, head and tail would come, but you can very well understand that the possibility is head and tail together, so the number of cases would be 2, but the favorable case for H is what? 1. Again, for the second case for tail, the head could come, T could come, so 2 is the total number of cases, but the favorable case T, that is 1, so half and half. If you combine them, PH and PT, it will be equal to 1. What if we assign PH as 1 by 4 and PT 3 by 4? This is also true, no problem, because 1 by 4 plus 3 by 4 is again 1. This actually abides with what we have learned in the axiomatic rules. So now one thing I would like to tell you, that if something happening is having a possibility of P, then the not happening of this will be 1 minus P, because the maximum can be 1. If you combine them, you get the possibility is 1. So possibility of happening one event and not happening of that event, if you combine that, you'll get 1. Okay. So there are a number of ways you can combine. There are infinite ways actually. So let us take an example. So this is an example. This is a sample space W1 to W6. So there are 6 elements in all. W1 to W6 in the column you can see. Now, which are we have assigned certain probabilities. You have to tell which of them are valid or invalid, as we have just seen the axioms now. See, first thing is every possibility W1 to W6 should be between 0 and 1. First thing we need to check this. And the second thing is, if we combine them, it should give you 1. If you combine all these, add these, it should give you 1. So if you combine 1 by 6 times, it will give you 1. So this is okay. If you combine this, all are between 1 and 0, 1 and 0 inclusive. And if you combine them, it will give you 1. So it is also okay. What about C? See, these are the negative numbers. We cannot take this. This is unacceptable, because the probability has to be between 0 and 1, each probability. Next is D. See, this 3 by 2. This is 1.5. You cannot have 1.5 because it can only be between 0 and 1. The next is, okay, these probabilities are fine, but if you combine them, it is going to give you some number that is 2.1. So this is not acceptable. This is not valid assignment. So probability of an event, Say you take an example, that is, you want to examine some pens which are coming out of a machine, and you want to tell that whether these three pens are defective or not defective. So all the pen can be defective, all the pen can not be defective, one can be defective, one pen can be defective, two pen can be defective. So these are all the possibilities. So let us make a sample space. You know by now how to make this sample space. There are 8 elements here. So if you want to assign the probability of all to be BBB, that is all to be defective or bad, this will be 1 by 8, because the favorable of this is 1 and the total number of elements are 8. So all these have a probability of 1 by 8. Now if you say I have some other event, say A is the event of exactly having one defective pen, so all this will have 1B, 1B, 1B. And the next one is there are at least 2 defective pens. So we have 2, 2 and 2 and 3, because at least means at least it should have 2B, it can have 3. What about this? What is the probability of A? This is 1 by 8, 1 by 8, 1 by 8. So 1 by 8, 1 by 1 by 8 is 3 by 8. What about this? 1 by 8, 1 by 8, 1 by 8, 1 by 8, that is 1 by 4 by 8, that is half. So there is no problem. These are absolutely fine. What about tossing a coin twice? HH, HT, TH, HT, TT, you have known that this is the sample space. Now what is the probability of having HH? Let us give it as a probability of 1 by 4, 1 by 7, 2 by 7 and 9 by 28. So there is no problem, because all these probabilities, they lie between 0 to 1. If you combine this HH and TT, say you have another event, say both the tosses, it would give you same result. So HH, TT, so it will be what? 1 by 4 plus 9 by 28, 4 by 7, this is also okay. No problem with them. Exactly 2 heads, this is what? This is also okay. So probability of equally likely outcomes is what? Say if you have an event like H and T, you cannot tell. You have 50-50% probability that H can come or T can come if you toss a coin, fair coin. Then if you combine these, because they are absolutely giving you equally likely matter. So if you combine this is first will have probability of P, then P and N times. So if you combine them, this will be NP and this is equal to 1. So P will be equal to 1 by N. So ultimately what we have come across by discussing this, if S is the sample space and E be the event, so the number of element in S, if it is N, and number of element in E is M, probability is M by N. M is the number of outcomes which is favorable for E, this event, and the sample space event, that is the total number of or total possible outcomes. This is our probability. This is actual probability we have been learning, and this is what we are going to use. What about probability of event A or B? Either A or B. Let us take two sets. A is this, B is this. And if we these are the event associated with if you toss a coin thrice. So A union B is what? These three and one more. So this is the A union B. What about P A union B? Probability of A union B? P of this, P of this, P of this, P of this. Okay. So what you get? These are, because you know that if we make a sample space of this event, it is going to give you total number of 8. And what about this? This is one element. So 1 by 8, 1 by 8, 1 by 8, 1 by 8. If you combine them, it will be 4 by 8, that is half. So probability of A union B is now 1 by 2. When we combine PA, different, means the only A element, it will give you 1 by 8, 1 by 8, 1 by 8, 3 by 8. If it gives, if you take PB only, 1 by 8, 1 by 8, 1 by 8, that is 3 by 8. Then you combine these, PA plus PB. It will give you 6 by 8. So what we got? PA union B was what? PA union B was half. While if you combine them separately, PA plus PB, it will give you 6 by 8. This is not equal. This is not always the case. I'll tell you when this case is. But you must remember that this is not equal. Why? Because we have these two common also. Means if you take intersection of these two, you will get values as common. Like this HTH, like this THH, both are common. So intersection is there. So you are actually adding these twice. When you are adding PA plus PB, you are actually adding these two twice. in the elements of A and A intersection B, you are adding here twice, so you have to subtract it once to get the exact result. That is why 6 by 8 was not equal to 1 by 2. So when we subtract it, that is, you have to subtract PA plus PB by the extra added PA intersection B. This is our expression. This is, you have to learn, PA union B is equal to PA plus PB minus PA intersection B. Now you'll say, okay, this was fine, but I would like to do it mathematically, not just by, okay, you have added it twice. So what we can do here is, we take this, right, and now we are going to prove it mathematically. For that, we have to go to this figure. Please understand, this is A total, this is B total, this is A intersection B, this is what? A minus B, this is B minus A. So all these three are mutually disjoint, or you can say mutually exclusive. So we'll use this property here, and we'll come up to our discussion, our expression that we have just seen by observation. So A union B is what? A union B minus A, as you have just seen in the Venn diagram. Because A and B minus A are actually mutually exclusive, as I just explained you. What about B? B is nothing but A union A intersection B union B minus A. You can verify it, right? You can verify it here. So these two expression. Now let us take the probability of PA union B. So this will be PA plus PB minus A. What about this? PB is going to give you PA intersection B plus PB minus A. Now subtract these two. You'll get PA union B minus PB is equal to PA minus PA intersection B. Rearrange them. You'll get PA union B is equal to PA plus PB minus PA intersection B. Exactly the same thing. Exactly the same equation as you got here. This we did by observation, and now this we did by our mathematics, like using Venn diagram set mathematics. So this is the actual equation that you have to use. But we'll see that when this is going to be empty or zero. How? Because when these two are A and B are disjoint, that means these sets are like this. There is nothing common. When there is nothing common, A intersection B doesn't exist, so it is empty. So P of empty is 0. So you have to put this P A intersection B. This is actually 0, so just place 0 here. So you'll get PA union B is equal to PA plus PB. So at this case, as I just told you in the earlier discussion, that this was not equal, but it is not always the case. If this is going to be 0, then it will be equal to PA plus PB. So this was our discussion about axiomatic. We'll be taking more discussion on this later on in the next session. Thank you so much. Take care of yourself.